these convection radiation is coming out of the materials or anything that the wall or anything that is radiated out, that is also calculated. The existing air temperature is calculated, the velocity, the relative humidity, everything is put together, and also the person's perception. Their metabolic activities will also release some kind of temperatures, and also the clothing insulation, like how much you are actually protected from the kind of cloth that you use. All these aspects are put together to get the thermal comfort.
Any more questions?
What are your proposed solutions for such cases, since these type of buildings are spread out in Kerala and in many spaces? What are the proposed
So that is going to be the next part of my study. So this is my pilot case study where I have to prove that there is an issue in Kerala, and from this I will move forward to my actual case studies where I will be doing a lot of simulations, making a lot of changes in the kind of building envelope, also maybe with the materials. So from that I will be able to propose that these are the kind of guidelines that is required when you actually develop or design an industrial building, because as of now there is no guideline for industrial buildings.
Thank you.
Thank you so much.
Thank you so much. Our next presentation will be about the tailored nano composites for dual function electrochromic and energy storage devices toward net zero buildings, presented by Dr. Muhammad Nur Hafiz Mustafa, who's a lecturer at Sunway University in Malaysia, and his research is mainly focusing on developing innovative materials for smart windows that respond to electricity, light, or temperature changes. In his presentation, he will show how the tailored nanocomposites material will be used to enhance the electrical conductivity and electromechanical performance. Please go ahead.
I can give you my account number. You got the key? Yeah. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good day. My name is Hafiz from Malaysia, our university. So today I'm going to talk about tailored trimethyl phosphate combined with Maxine, which is a composite for dual application, electrochromic and energy storage device towards the net building. Sorry for the hiccup. Okay, first, this is Sunway University in 1979. We are just a teen mining from that. From wasteland, so we convert to the wonderland. Today, in 2035, this is our city, whereby we have the theme park, we got the hospital, and also our university located here. This is our university on the left-hand side. So, let's talk about today's presentation. So, the motivation for today is we are trying to solve the building that consume more than 40% of global energy. So, we are trying to find something that need to focus on this problem, which is providing a net zero solution. In this case, what we are trying to do is we want to try to combine two applications, which is electrochromic supercapacitor. Maybe a lot of you already know about supercapacitor, the ability of the device to store charge. But electrochromic is the ability of the device at the same time change current. for the small potential applied. And this application can be combined because field mechanism is overlapped. Because both of them undergo redox process whereby ion changing from charging and discharging, so we can produce electrochromic supercapacitor device. However, for the current materials, there is a lot of limitation. When focusing on one application, for example, electrochromic, like tungsten trioxide, nickel oxide, they have good optical change. The color can change very fast, very beautiful color. However, the energy storage is very poor because of ingression, regression, oxidize, reduction. This limits your material. Your material becomes fatty. And for supercapacitor, on the other hand, the traditional carbon, graphene, polymer has very good storage, very good stability. At the same time, there is no redox there. It's just what we call that there is no optical response there. Then moving to our solution, we try to combine this material. First of all, is bimetallic phosphate, combining two metal oxide, whereby these two metal oxide have rich redox chemistry. We are telling about nickel 2+, nickel 3+, or 2+, and 3+. The more the oxidation states, the high chance for high charge storage capacity. And why at the same time MXenes come into the pitch? So MXene in this case, because MXene is new 2D material that coined to replace the graphene. One of the properties is the metal conductivity, enhanced electron transport, and the best thing about MXene compared with graphene is hydrophilicity. It can dissolve in the solvent, such as water. So here we cover about SDG7, followed by clean energy, 11, and also last but not least is about climate exchange. So that's our motivation. Let's go a bit into the synthesis of our material. So in the material, like if you already know, the traditional hydrothermal takes a long time. So the idea is to introduce a microwave, very simple, straightforward, and very fast. As you can see, for example, here we put our precursor into the microwave, and you see the holding time only 10 minutes. Less than half an hour, you can get your material. And for MXene itself, the same technique we are using for microwave, but involves 3 treatments. HF treatment to remove the extra aluminum. Because titanium aluminum carbide is nothing, it's nobody. It's a matte phase that is not conductive. You use for cement. But to be included into the conductivity, we need to remove the aluminum, become titanium carbide. And then the second process is delamination. Because the normal MXene, the structure is exfoliant. So when you do the delamination process, you can get a single exfoliated MXene, which is trusted and to get a good performance in our material. And last but not least, the preparation for titanium powder by using the centrifuge and also freeze dry. Combining the two materials, we are using the simple spin coating technique, whereby here we utilize and we do the optimization on the material concentration, and then we put into our device in 3 electrode system and also in 2 electrode system in the thin film technology. Okay, that's on the optimization. Move on how we optimize. So have you heard about response surface methodology? Okay, this is ANOVA for our material, whereby here we can see when we focus on the model and model term. So the model shows a significant when model A, the factor is the concentration of the nickel cobalt phosphate, factor B is the concentration of MXene, and this factor is significant toward our surface response, which is specific capacitance. And see, after that we do the validation test, we got the RSC less than 2%, indicating 98% confidence level of the model suggested by the optimization. Okay, this is the graph they show you from the optimization. Focus on the graph C is the 3D graph between each independent parameter towards the surface response. The more curvature of each independent parameter toward the surface response indicates that the model is reliable, which is quadratic model suggested by the ANOVA. Okay, next move on to the conformational analysis. We need to confirm our material. So we are talking about bimetallic phosphate combined with MXene, how the material is truly combined. So here I'm only highlighting two analyses. The first one is about XRD. From the XRD we can know it's confirmed with phases with nickel phosphate, cobalt phosphate, and also titanium carbide, and match with each JCPDF number. And from that we are saying that our material is successful synthesis via our method, and we also calculate the crystallite size using the Bragg method, and the size is around 111 to 145 nanometer. And for FISM, it's very beautiful. When you see the first one is nickel cobalt phosphate, is a flower-like morphology. For titanium carbide, is a nanosheet structure that confirming successful delamination process, and combining, you can get a flower line. On top of that, you can get nanosheet structure. And this, as a material chemistry, physically is confirmed the presence of your material. Okay, move on to the performance. So we are talking about how high it can achieve the energy storage. How efficient is it? So that's why we move to the performance analysis. So basically, we are dealing with 3 electrode system and 2 electrode system. 2 electrode system is for the device. 3 electrode system is for confirming the material is good or not. So quickly, let's go one by one. For CV, this is cyclic voltammetry. For those new to this, for electrochemistry, this is a good analyzation. When from here, you can actually measure the charge storage capacity based on the area under the graph. And to make it easy, I already plot to you from the CV, the maximum specific capacitance achieved by the material is 2,270 farad per gram. And upon increasing the square rate, is reduced up to 700. So why this happen like that? So we are talking why, because at high square rate, the ability of electrolyte ion to go into the bulk of the material is very hard, because it don't have enough time to penetrate the bulk of electrode material. If you learn about supercapacitor, the basic thing, we're talking about EDLC, occur at the surface. And then we talk about pseudocapacitors, and also battery type material that can go into the bulk of the material. That's why increasing the square rate, reduction occur on the capacitance with limited ion diffusion at higher square rate. Okay, then you might ask me, how we confirm that? So we do the Dahn method and study the different mechanism. By the Dahn method, we can know that at 1 millivolt per second is diffusion limiting process compared to the high current density. Okay, move on to the second part, which is the electrochromic. So we just talked about energy storage. So for electrochromic, it's about the color changes. Okay, this is our material. It's changed color when we apply different voltage at 0 volt and also 0.5 volt. We measured by in situ absorbance, whereby what happens is when you apply at 0 volt, you can get the dark color here, the black color, low absorbance. And at 0.5 volt is charging, it's more opaque. That's why your absorbance becomes increased. When you compare to the transmittant, the result is vice versa. Because transmittant is more opaque, means that the transmittant is very low. So this we do for 1000 cycle and measure the optical contrast retention. Okay, that's for our 3 electrode system. And last but not least, on our device. So we do on our device for galvanostatic charge discharge, is a charging and discharging mechanism. Study the stability on retention and also plot the Regen plot and compare to the rest of the literature published. And for this, we combine to form our device, our material with activated carbon. And the result shows that the energy and power density, the maximum we can achieve is 14.5 watt-hour per kg at 1500 watt per kg and its power density. And when we compare with Maxim-based device, we can see that the material is comparable. And to conclude, dual function already achieved in one single device. We successfully combined electrochromic and supercapacitor. We achieve a very high coloration efficiency. The meaning of high coloration efficiency is the ability to change color, and also the energy density comparable to the state-of-art on Maxim device. So I think that's all. Okay, thank you. If you want to do the collaboration, you can scan the QR. Thank you very much.
Thank you so much.
to metal, then you expect there's a synergy effect.
Yes,
In
correct.
this case, what is nickel doing and what is cobalt is doing, and what is the synergistic effect?
In order to talking about the synergistic effect, because this one I put just small graph. Before that, we need to compare with a single nickel and single cobalt and compare the graph with the cyclic voltammetry. So what happened is, when we accumulate both have different oxidation states. In electrochemistry, when you have more than one oxidation state, you can generate more electrons. That's why in this case, combining both can enhance the energy storage performance. And we also further analyze that with the Dunn method, with single material and double material. And the performance showed that the energy storage for double material is more than single material.
Why? That's the question. Why?
Yeah, because the existing of more energy storage, more what we call that states on the material because of that. Because in energy storage, it depends on your electron, how much you can store. So, but the drawback is if you give too much redox, the stability will be dropped. That's the key point, how you optimize. That's why we use the RSM to optimize the concentration of each material. Okay, I hope it's answered.
Thank you. Thank you so much. Thanks. Our next presentation titled A Two-Stage Method for Recycling Concrete Aggregates from Construction and Demolition Waste, Fostering a Circular Economy, presented by Dr. Mohamed Noor from UAE on behalf of the Ali Cycle.